Okay, cool. I think we can get started. So my name is Andrea, and I'm going to present you what you can do in terms of pipelines in FCS Express 7 with imaging data. Today with me online, Robin, one of my colleagues, and she will also help me today to answer a question in real time. So again, feel free to navigate to the question section of the GoToWebinar dialog, and feel free to type in any question you want during the presentation. So either me and Robin, we will try to answer in real time. If there will be no time to do that, we will follow up with you at the end of the presentation. Yeah, I still see people connecting, but I think we can get started. I have a few slides of introduction. Okay, so today we will speak about image cytometry data, FCS Express 7, and you will see what I meant with pipelines, which is a really cool and very new tools that we developed. It took us almost 1 year to develop it, but it's really great. It's like a game changing. So this is the agenda for today. I want to spend a few words on the image version for those of you who never tried FCS Express for image. We will see what's a pipeline and how does it usually look like. And also we will see how it look like in FCS Express, which it's really much better. And also why pipelines are so powerful and why we decided to implement pipelines in our software. Then we will move to FCS Express 7. So no longer slides. We will play with some data. We will see how to create pipelines, how to add steps to the pipelines, and we will do this with some practical example. Okay, as you can see here at the bottom, I I I did this, let's say, selection because I think it covers more or less most of the calculation and the transformation and the steps that you might need. But we have so many steps that it's barely impossible to go through all of them in 1 hour. Okay, so a few details about the image version. So FCS Express for image give you the ability to analyze image data in the same way you can do with flow data, meaning that you can create plots, and we have tons of different plots type. You can create gates, markers, quadrants. You can access an integrated spreadsheet to make calculation. You can access map, and of course you can also access the picture. Okay, how can you make your data compatible with FCS Express? So it depends on the instrument that you're using. So as you can see here, FCS Express can deal with segmented data. Okay, if you just import a picture in FCS Express, FCS Express just treats that picture as like a JPEG, a TIFF, or whatever. So what you need to do is to first segment the data so that FCS Express can really access every single cell in that picture. This is done for some instrument directly with the acquisition software. You can see this IC format. It's the standard. Let me highlight it. This IC format is the standard in image cytometry data analysis. It's like the good friends of the FCS file format in flow cytometry. And there are a bunch of instruments that can save in this format. So if you have one of those instruments, you can just import the IC file in FCS Express. Then we have a bunch of instruments that collaborate, a bunch of companies that collaborated with us so that we can open the proprietary format. Okay, we will use an example also from a company from this list. And last but not least, if you do not have an instrument among them, okay, no worry, you can grab any picture you want, okay, even a picture that you took with your mobile phone, and you can segment that picture with some free software, for example, Cell Profiler and Image. Okay. So no worry, we are really flexible in terms of data analysis. So again, the idea is that you do the segmentation here in either in the acquisition software or in external software like Cell Profiler or Imaging. And once you have single cell data, then you can go to FCS Express, and you will have access to all the numerical values, so the features, and also to the single cell value, to the single cell picture in FCS Express. So that's super, super, super powerful. Now, today, again, we will speak about pipeline. So we need to introduce what a pipeline is, of course. So pipeline is a set of data processing steps or elements or blocks. Okay, and they're usually mathematical calculations. And the main point is that first, they are connected in series. Okay, as you can see here, we have a step A, step B, step C, step D. Okay, and from A you go to B, from B you go to C, and so on. And the second really important point is that the output of one step, okay, let's say that one step transform all the data in log scale. Okay, so at the end of that step, let's say step A, you have log scale data. Okay, the output of each step is usually the input of the subsequent step. So if A transform your data with log, okay, B, it's probably using the log transformed data. Okay, actually, B usually access either the log transformed and the original data. But what you usually want to do is to use the log transform at that point. Otherwise, why you log transformed in step A? Okay, so again, the key point are that steps are connected in series, and usually the output of one step is the input of the next step. Then, it's good to know that most of the algorithm used in usually high dimensional data analysis, so we will see some example today, like tSNE, optimized tSNE, FlowSOM, SPADE, UMAP, they're pipeline themselves, okay? So the programmers that develop those algorithms actually create multiple steps. So pipelines are really, really, really diffused. Okay, pipelines are something that developers, like statisticians, mathematicians, they are using every day since ages. Okay, and you will see why we decided to implement this way of analyzing data in FCS Express. Then another good point of pipelines is that pipelines can also be combined together. So you might have a pipeline and you say, oh, wow, I have my super nice pipeline, which is A, B, C, and D. And then you realize that with this pipeline, you can you can use this pipeline as a single, let's say, step of a much longer pipeline. Okay, so the beauty is that you are super flexible, super powerful, and basically there are infinite pipeline that you can create, okay, with a lot of step in infinite like orders. This is the real power of pipelines. So usually a pipeline looks like this, okay, which is not super user friendly, I will say. Okay, this is what you see, for example, if you're coding with R, with Python, or whatever. So of course we're not asking you to deal with something like this, and you will see how we implemented pipeline in FCS Express, and you will see it's a much user-friendly interface. But you may ask yourself, so why statistician and bioinformatician and mathematician would like to deal with something like this? I mean, it should be really powerful, because if you are let's say accepting to work with something like this, and yeah, it's really like that. So the beauty of the pipeline, as we said, is that they are super flexible, because you can combine different steps together, okay, and generate a different output. Okay, I won't have A, B, and C, and maybe one of you want A, B, C, and D, and maybe another one would like B, A, and D, whatever. So combinability, flexibility are the main point of the pipeline. And if you think about that, what you're doing in data analysis, it doesn't matter whether you're dealing with flow or image, but basically you are doing the same, okay? You're always going through a bunch of almost predefined steps. Okay, so you have some keystone, like you start with your data, let's say the IC files or whatever, or you start, I don't know, like cleaning up. You want to select a specific population, or maybe you want to deal with all the pictures, so all the events that you have in your region of interest. You need to select the parameters. Okay, usually in imaging data, you have really a lot of parameters, but maybe they are not always and all useful for the calculation that you are going to implement. So you need to select parameters. You need to scale parameters. This is really important. Okay, maybe you also want to normalize them. Okay, downsampling I've listed here, but usually uh, it's it's not going to be used as the downsampling like in flow cytometry, because first of all, in imaging, usually you have less data point than in flow, but especially you don't want to downsample, probably because you want to have access to every cell in the picture. Okay, you don't really want to have any hole in the picture. But still, downsampling it's one of the pre-processing steps. I will show you an example of downsampling that might be useful. So this is the pre-processing part of the analysis. Okay, it's anyway a pipeline itself. Okay, because you are selecting, so you are filtering some parameter, you are filtering some cells. Eventually, you are normalizing, and then you are scaling and whatever. At some points, you have your scale, normalized, clean, and whatever data, and you start running the core part of the analysis. And the core part might be some clustering, some dimensionality reduction, and whatever, maybe both. Okay. The beauty of the pipeline is that since you're not running your algorithm as a standalone algorithm, okay, let's say you're not running tSNE on its own, and then UMAP on its own, and then FlowSOM or any other clustering on its own. So you are running all those guys into the same pipeline. This means that if you first run, I don't know, UMAP, okay, we will use UMAP later on as an example of dimensionality reduction. You are generating new parameters called UMAP 1 and 2, okay, because those are the X and Y axes of the UMAP map, okay? And maybe you want to cluster based on UMAP 1 and 2. So the clustering will access the output of UMAP 1 and 2. If you run, on the other hand, if you run the clustering and UMAP as a standalone algorithms, okay, they will not, let's say, speak each other. Okay, they will be independent. So the beauty of the pipeline is that you can combine those algorithms into the same workflow. The last part of the workflow, it's usually like the data presentation, or maybe some summary statistic. Maybe you want to do an ANOVA t-test or Mann-Whitney, some statistical analysis, some charts, I don't know, box and whisker or whatever. So this is the whole workflow, and this is why we spend like 1 year to 1 year to implement pipeline in FCS Express, because we want to provide you with the ability to run all the stuff inside the software without like exporting, or even worse, like copy and pasting or whatever. Okay, so this is the idea. And of course, we wanted to provide you with a user interface that was like much more user friendly than what we saw before, like a black screen with some coding line. So we wanted to provide you with something which is easy to use, which is fast, and this is really important. And again, combinable and reproducible, those are really, really crucial points. So reproducibility, it's really important. So think about if you need to accomplish your workflow, like 3 or 4 different software. Okay, you have your like data analysis, and then you export as a, I don't know, CSV or whatever, and then you go to R, and then you generate some output, and then you import this output in a GraphPad and whatever. So it's really hard to keep track of all the different steps. Okay, it's really hard. If you have everything integrated into a unique platform like FCS Express, it's much easier because everything is in one single file, which is the layout of FCS Express. So graphically speaking, this is also our goal. Okay, so in the same layout that you have in a in which you have like plots and gates and whatever, you might have some dimensionality reduction, some clustering, some charts, and of course, you can access the single cell picture or the whole picture of that you took from the microscope. Now, how can you access the pipeline in FCS Express? We will do this together, but I already want to introduce you to this transformation dialog. So this is FCS Express. We will not have so much time today to go through all the basics and the statics of FCS Express, but for those of you who are new to FCS Express, just consider that it's really like PowerPoint, okay? It's like PowerPoint first in terms of aesthetics, okay? You see, this is a screenshot from FCS Express. You see that at the top, you have a ribbon bar, okay? You have a File tab, you have a Home tab, you have the Insert tab, you have the Design tab, and blah, blah, blah. The second is that also the way in which you are putting together the analysis, it's really similar to PowerPoint. So in PowerPoint, if you think about that, you open PowerPoint, you have a blank page, and you start adding object, right? If you want a title, you put a title. If you want a picture, you put a picture. If you want to make the picture bigger, that's fine. You can do that. So in FCS Express is the same. If you want to start with a title, you will create the title, and then you will create one plot or maybe 3 plots in a row, and maybe a big histogram. That's fine. You are putting together the final results as it will be a PowerPoint presentation. But of course, it's much more powerful because everything is live updating, as you will see in a while. But anyway, let's go back to the pipeline. So under Tools, okay, the Tools tab, you have the Transformation dialog. Okay, and the transformation dialog is this one. As you can see here, you can click on plus and add transformation. So you can access to the old, I will say old-fashioned nowadays, so old-fashioned standalone transformation like K-means, PCA, Spade, and tSNE. Those are the standalone ones. So either you run tSNE or you run Spade, but anyway, you can also run all of them, but they will not speak each other. Nowadays, people will always run pipeline, okay? So this is why we are here today. And once you create the pipeline, you will be able to start adding steps, okay? And this is done by clicking on this other little plus. We have about, I will say like 40, 50 steps. So we are going to add more steps based on your feedback. And we grouped different steps, similar steps in different category. Like, as you can see here, we have a category that says predefined algorithm, and we added here algorithms that are pipeline themselves. Okay, so for example, Flow AI, which is a quality control algorithm for flow data, FlowSOM, which is a clustering, Spade, which is a clustering. Those are pipeline themselves. So instead of creating this algorithm by adding step by step, maybe like 5 step, 6 step, we already created a one-click version of that algorithm so that all the step composing those algorithms will be added here, okay, automatically. We will see an example with FlowSOM later on. And then you see we have downsampling. Again, you might not need downsampling in image cytometry data analysis, but it's good to know that it's there if you're also dealing with flow. Dimensionality reduction, clustering. For dimensionality reduction, as you will see, we have like PCA, UMAP, and tSNE of tSNE. For clustering, we have a bunch like hierarchical clustering, consensus clustering, K-means, SOM. We will have a new version of SOM, which is used by FlowSOM, and we will have a new version which is even faster. It's really amazing. It will be out in the next release. Then we will have visualization. This is great if you're dealing with clustering because you can visualize cluster in nodes. You might know, for example, the FlowSOM, it's like a node, a tree made of nodes, something like this. Okay, you can do this with any type of cluster. So that's the beauty. You can use the same strategy that FlowSOM or Spade are using to create the FlowSOM or the Spade tree to plot the clustering that comes out from, I don't know, a K-means or hierarchical clustering. It's really up to you. We will spend quite a lot of time for go more in depth in the mathematical steps, because few of those steps are really beneficial for most of the algorithm that you might want to use. And for example, the scaling step. Then we have some quality control. These contain like 3 different quality control. They have been developed for flow data, but I'm super happy to show you that one of them can also be used somehow to analyze image data. And then we have miscellaneous. We will see an example at the end. So anyway, go to tools, go to plus to create the main pipeline body, and go to plus to create different steps. This is exactly what we will do. So you don't need to start with, I mean, you can, but you don't really need to start with some very complex pipeline. A pipeline can also be like 2 steps or even 1 step. So no worry, take your time, play with your data, and start with something easy. And you will see that after very few tests, we will be able to run some quite cool pipelines. So the main pipeline body, so when you add this step, okay, this one, this is called main pipeline body. This is pretty simple dialog. It just allows you to do 3 things. The first one is selecting which is the input population, okay? If you have a gates, if you want to remove some, I don't know, maybe you realize that the segmentation was not really perfect. You have some events that are artifact, maybe they are super small, super big, or whatever. You can create a gate to exclude them, let's say, and then you can focus on that gate. Okay, so it's not mandatory. Okay, you can select the gate, or you can also keep the no gates. It means that the pipeline will be run on every event. Then you have the selection for the input parameters. So this is the overall input parameter list for the pipeline. Okay, it's not the parameter list for specific steps. So usually my suggestion is just do a right click and select all, so that you will have access to all the parameters within the pipeline. Then every step will allow you to select which parameter you want to use and which not. Last but not least, you have the ability to define a suffix. So you will see when you will apply a pipeline on a plot, the plot's title will report this suffix. Why this? Because you might want to create multiple pipelines. This is 1, this is 2, this is 3, this is 4, whatever. Okay, those are 4 different pipelines. I can call them pipeline 1, 2, 3, and 4, so that once I will apply them to my plots, I will clearly see which pipeline is applied to which plot. Okay. Last but not least, I should have said that through this dialog you can do 4 stuff. This one is pretty useful. So everything in FCS Express, it's set to be to live update. Okay, every tiny change, every time you move a gates, every time you like change this dialog, change something in this dialog, everything trigger FCS Express to live update. If you are dealing with let's say a very huge and big and slow pipeline, because you have a lot of calculation, and let's say you need to uncheck or check 4 different checkbox here. Okay, instead of clicking 1 and wait, clicking 2 and wait, clicking 3 and wait, clicking 4 and finally wait and get your results, you can deselect the automatically run pipeline, uncheck those, and then click it again click on execute. So it's just a way to defer the live updating for a while. It's pretty useful. Okay, so there are different category, like as I said before, like quality control, mathematical, downsampling. And the first example that I want to show is about the quality control. Again, these steps, the one that you see here, actually are there because they are part of a predefined algorithm called FlowAI, which is a very popular algorithm to perform quality control on flow data. But actually, FCS Express is so powerful and so flexible that give you the ability to run even just one part of that algorithm. So that algorithm is based on 3 different steps. Okay, but the beauty is that with the pipeline you can let's say separate all those steps and just run the one that you want. So as an example, I will use one of them, which is the dynamic range and downsampling, which is I mean, it's a good example in case you want to set some threshold. Okay, you say, I know that I have some outliers, maybe something which is really small, something which is really high. Of course, I can place a gate. I can put a gate and say, okay, from this region on, I want to remove everything. But I just want to show you what you can do with the pipeline. Okay, so let me open these layout. So in this case, in my layout, here we go. It's opening on my second screen. No worry, here we go. Okay, so oh, it's this one. Too many stuff. In this example, you see I have my plot of interest. Okay, it's a very basic pipeline. I just have one plot, one gate, and few cells, just to show you that these come from image stream. You see, I can gates here. I can apply gates. I can move my gates. My single cell table here at the right, it's updating live. So I can also gates on one single cell here. Okay, but anyway, let's say that for some reason you want to exclude some very small events. Okay, we have this parameter area MO2, and for some reason we want to set a threshold here and remove everything which is below this threshold. Okay, we can do this with the pipeline. Okay, again, the pipeline can be really simple. Okay, you don't really need every time to have like 20 different steps and clustering and whatever. Okay, so we know that you need to go to tools and open the transformations. Transformation is now empty. I'm going to click on the left blue button at the left and click on pipeline. And this is our well-known pipeline main body. Okay, I don't want to set any gate in this case. The software use this file. Okay, this is a DAF file. This is the selected plot to retrieve the parameter list. You see, I have a lot of parameters in this list. Okay, I'm going to right click and select all. This is the suffix. As soon as I will, let me move this a little bit here. As soon as I will apply the pipeline on my plot, you will see that this suffix will be added to my title here at the left. Okay, I will make this plot a little bit larger. Okay, so you will see the suffix at the end. Okay, so now we have selected the gates, no gate. We have selected the parameters, everything. We defined the suffix. I just kept the default one, pipeline transform, and I can add steps. Again, just to review, we have predefined step. If I add Flow AI, I will add 3 steps that are actually this quality control. But today, with this data, I want to show just one of them. Okay, just to again reiterate that the main advantage of the pipeline is the flexibility. I'm going to click on dynamic range, and this is my dynamic range step. You see that now I can select which is the input parameter for this specific step. And this list is as long as the list of parameters that we selected in the main pipeline body. So if you do not select a parameter here in the main pipeline body, you will not have access to that parameter in the specific step. So that's why I told you, I suggested you to select everything there. Okay, we want to work with the area MO2. So I will click on area MO2. And what we're doing is to set an upper and a lower limit. So by default, this step again belongs to an algorithm called Flow AI. So we are using the same setting of that algorithm. But you see, you can uncheck those 2 checkboxes and set the upper and the lower limit. Okay, let's say that just for fun, I want to set my lower limit somewhere here, like this should be like 70, and the upper limit, it's okay, like 1000. Okay, I will type here 70, and here it's 1000. Now, how can I run my pipeline? Okay, the pipeline can be run on a specific plot. Again, this is useful if you have multiple pipeline and you want to apply them to different plots and to compare. And you can do this by, let me draw here. You can drag and drop the pipeline on top of a plot, or you can select the plots and click on this button here. Okay, this button says apply to selected plots. If you want to apply to all plots, just click on apply to all plots. Okay, either way, just do what you prefer. Now, I'm going to use drag and drop. Okay, now the pipeline is applied. Let me see here. Oh, sorry, this is inverted. It's okay, I mistyped. So this is the upper limit and this is the lower limit. So you see here, the upper limit it's still 1000, but the lower limit now it's 70. Okay, the result is that I basically got rid of all the dots that are below 70. Okay, so it's different than a gate, because with a gate you're focusing on a region but you're not really removing the other dots. Okay, this is actually a downsampling because you are really removing all the other dots. So after this step you will only have access to these events. Okay, and it's live updating. So if I say like 60, okay, it's updating live. Now it's 60. If I say like 40, okay, it's updating live. So it's really fast. So this was the first example of pipeline. It's just one step. This is just like a threshold that removes everything at the top or at the bottom. Okay, if you have any question, please do not hesitate to write in the chat. Okay, let me close this and let me go back to my presentation. Okay, so the next example of pipeline, it's under mathematical, and we have quite a lot of interesting stuff here. So under mathematical, I will show you these three guys. Okay, scaling, this is super important. Okay, most of the algorithm benefits from a scaling step. And then we will also have a look at the normalization and the 0-1 scaling, okay? But you can already have an idea of what these steps are doing. So in this case, let me see if I can zoom in a little bit, okay? In this case, yes, I can. In this case, the data are saved as raw data, you see in the plot at the left, and raw data in this case are saved with linear scale. But look, if I apply a log scale, my data looks much better, okay? And this is not just applying a log scale to the axis, as we are usually doing. In the pipeline, data are really transformed, okay? So these CD4 goes between 0 and 186.5. If you log transform, okay, you see that the number are completely different, okay? This is 186.5 in log transformed. Okay, then if you normalize, okay, meaning that you are dividing by the standard deviation and subtracting by the mean, okay, these data will now be centered on 0 and will have a standard deviation of 1. So you see the number is slightly different. Okay, and if instead of the normalization, you do something different, okay, you can do also both. But if instead of the normalization, you do like the 0-1 scaling, okay, now you see that the range of data, it's forced to be between 0 and 1, okay? I'm changing the actual data, okay? Usually when you're applying a scale on your histogram, you're not changing the data. It's just something aesthetics. You're just changing the scale of the axis. The pipeline actually transform your data, because when you're going to run your algorithm, the algorithm doesn't really care about aesthetics. They care about numbers. Okay, so let me go here and let's do this together. Okay, you already know how to do this, but it's good to review. This is another example. This is another data set from another instrument. You see, I just apply some gates. I just draw some gates to show you the back gating. So you see that if I highlight cells, they will be red because the gate is red on my picture plots. Okay, but I do not really need this. It was just for show you that you can do that type of stuff. So this is my raw data. Let me do the opposite. I will make this smaller and increase it. This is my raw data. Okay, I will go to tools, transformation. I will create a pipeline, no gates, select all, and here we go, mathematical. First thing that I want to show you is the scaling. Okay, I want to scale these two guys, CD4, CY5, and FOXP3 FITC. So I will click on FOXP3 FITC and CD4 CY5. Which scale do I want? Automatic means that in this case means linear, because you see also it's linear in the plots. I don't want linear. I think it will be better log. Okay, so now if I apply the pipeline here on my plots, I will have access to new data. It's not like a downsampling that it's removing events. Here we are transforming some data, some parameters, and we are generating as output the transformed version. In this case, the scaled version of the data. So here I can load, for example, the CD4. Actually, let me do it in a new plot, so you will see the difference. Okay, this is CD4 scaled, and this is FITC scaled. Okay, you see that the numbers are different. Okay, now I can add a new step. Okay, I will switch off the automatic updates. I can add a new step, for example, the normalization. Okay, in this case, you see, since I have unchecked the automatically updates here, FCS Express, instead of showing me some out-of-date data, just made my plots blank. Okay, better to see blank than see something which is not updated. So we are doing this on purpose. Now, what I want to normalize, it's up to me, of course. I can normalize the original data, or I can do the normalization on the scaled. So the results will be scaled and normalized. Okay. And if I want to add a 0-1 scaling, okay, you see I can also drag it up and down, because depending on where I want to set this, I will access to different parameters. Now this is the last step. So actually I can apply the 0-1 scaling on the scaled or on the scaled and normalized. So it's really up to you what to do in this case. So now I'm scaling, and then either normalize on top of scaling or 0-1 scaling on top of scaling. You will see the results. Okay, so I'm going to click on automatically execute the pipeline. Let me switch it off for a while so that I have more room on my screen. And here we go. So at the very right, you have the original data. Then you have the scaled. Okay, here I want to show you the scaled and normalized. Okay, it doesn't change that much here, but you can see that the numbers are different. Okay, this is 2.2, this is 2.3. Okay, this is divided by the standard deviation and subtracted by the mean. And at the very right, now we are going to load the scaled and 0-1 scaled. Okay, this is this one forced to be between 0 and 1. Okay, makes sense? This is a good way, for example, in which you can make your parameters more comparable. Okay. I can see a question. So can you transform the data using a control sample to normalized? You cannot set a control sample in this case, because these type of transformations, so these scaling, are like based on some predefined calculation. For example, when you are divided by the mean, it's the mean of that. Sorry, when you are divided by the standard deviation, you are divided by the standard deviation of that parameters. So, for example, in this case, we divided all the CD4 value for the CD4 standard deviation, and then we subtracted the CD4 mean. And for the FITC, we took all the scale value, we divided by the standard deviation of the scale value, and we subtracted by the mean of the scale value. So it's within parameters. Okay, but that's a great question actually, and we are working to allow new normalization step to normalize based on a reference. Yeah, that's super interesting to do. Okay, so again, let me close this, and now that we know how the pipeline looks like, we can move on. And I just mentioned downsampling, but again, you're probably not going to use any downsampling in image cytometry data. Those really like reduce the number of events by keeping fewer events. It can be like random, interval, density dependent, whatever. But I didn't put together an example because I think it will be really, really rare if never used in image cytometry. Now, another example, it's dimensionality reduction. So there are two main family of algorithms that you can run when you're dealing with high dimensional data set. One is reducing the dimensionality. This is something that you can do with PCA. This is something that you can do with UMAP, with TreeMap, with OptSNE, tSNE, whatever. But basically, they are all doing the same stuff, okay? Which is really simple. It's really intuitive. You have a data set that exists in more than 2 dimensions, okay? Like in this case, and you want to go to a data set that exists in just 2 dimensions. Why this? Because you can plot in a map. So it's much more handy to have all your plots plotted in a map than dealing with a lot of dimension, because usually you don't even have 3, like you have like 5, 6, 7, 10, 20, 100, okay? So as an example, I want to show you UMAP. Okay, not because it's the best, just because it's I mean it's one of the available, and it's probably the most recent. No, definitely it's the most recent. Sorry, between them. And here we go. So we will start by creating a pipeline as we have already done, and we will start by scaling as we already done. Okay, so tools, transformations, pipeline. This is the same data set as before. And I will select all. I will not select any gates. I will keep the suffix. I will start by scaling, okay? This is not the 0-1 scaling. This is like log, B exponential, arcsine, whatever. So someone might ask, how do I know that a scaling it's better than another? So I think this is worth mentioning. I will show you as an histogram with this multi-plot histogram. I will show you something. So in this case, it's a very easy example. And again, I want to like work with, where is it? Fox P3 FITC, CD4, KI67. It's just 3, but you might have like 10, 20, 100, doesn't matter. Okay, so this is linear scale. How can I know that it's linear scale? If I select the plots, if I select all of them and I go to axis, I can see this is linear. Okay, x-axis on the histogram, it's linear. And I can already tell you that this is not good. This is not good because look at this, for example. This is CD4, it's really easy to see, okay? Those are the negative and those are the positive, okay? These peaks are not really comparable, okay? We are always habit to see something like this, okay? The negative and the positive. And this is not accidentally. This is because when you have homogeneous peak, it's more easy for us, for humans, to say, okay, this is the point where I need to discriminate between negative and positive. Okay, if you see something like this, it's much less easier. So if you see something like this, so what is the positive, what is the negative? Maybe the positive is this one, maybe the positive is all of these. So it's really less easy to do that. And it's even less easier if you are not a human and you are an algorithm. Okay, if you have something like this and you say divide it by 2, it will probably divide it this way. Okay, why instead you want to divide it this way? Okay, if you make those peaks more comparable, the algorithm will benefit from that. Okay, most of the algorithm will benefit. But anyway, if you have any doubt, just look at the internet, look at the original paper of that algorithm, write us, write the author, and whatever. But always ask yourself, do I need a scaling? Most of the time is yes. Then it might be the exponential, it might be linear, it might be log, but yes. So how this data looks like if I use the log? Okay, much better. Okay, I can clearly see these here. Okay, now they're more comparable, negative and positive. Okay, this is less easy to see because actually I don't even have a peak in the FoxP3. Okay, I have a broad expression. Okay, but anyway, this plot about FoxP3 it's much better now than before. Okay. Then you might face some marker in which it's anyway difficult to see. For example, you see the KI67, it's really broad, but anyway, with linear, everything it's compressed to the left. So this is a good way. It's a visual way to find out whether a scale is good or not. So let's go back to tools, transformation, and here we go, scaling. I will scale the FoxP3, the CD4, and the KI with log. And then I will add a UMAP from the dimensionality reduction. And guess which are the input parameters for UMAP? The scaled one, 1, 2, and 3. Okay. And now I can drag and drop on my plots. I can click on this one. Okay. I will click apply. And it will take a few seconds. I mean, UMAP, it's pretty fast. And this file, it's probably like 10,000, 15,000. I don't remember, but it should take like less than 10. And now you see that the suffix appear in my plots. Okay, you see pipeline transformed. Also on the picture. Okay, so if you do not apply the pipeline on some plots, those two plots will not speak each other in terms of the pipeline. So if you want, for example, to backgate, okay, you need to apply the pipeline on all plots. If you're dealing with just one pipeline in your layout, it's very easy, just apply to all plots and that's fine. So let me close these, okay? Let me just show you that now I have access to UMAP 1 and 2, okay? So this is a very easy example. Probably UMAP in this case, it's really too fragmented. Let's do something like these. I'm not really expecting so many highlands, but I mean, it's just an example. You probably have like 6, 10, 20 parameters in your case if you want to run something like this. So now that we have applied the pipeline on both, I can use backgating. So it means that if I create a gate on my UMAP at the left and that gate is red, I will be able to backgate those cells. Let's do it like this one. Okay, I will be able to backgate those cells on my picture plots. Now they are few, but I hope you can see some red events on the picture. Okay, and if I move these somewhere else, okay, you will see the red that are changing. Okay, so you can explore using the picture, or let me make some room. You can explore using color.plot. So I'm converting my UMAP to a color.plot, and I'm using these pretty cool features, multiplots. In this case, we are not creating multiple histogram. I'm creating an n by n, and I'm going to select my input parameter. Okay, so I will select where we are. Oh, sorry, CD4, KI67, and FoxP3. Okay, so it's a very simple. Okay, remember those are still linear. I can also open them as a scale if I want. So let me do this again. I will open the n by n, and I will go straight and select the last three. Okay, those are the scaled. Okay, and now I can backgate. Okay, so those one are FoxP3, FITC, very bright. Okay, and those one are, I don't know, intermediate here. Okay, it's just an example, just to show you that you can use backgating and color dot plots to navigate. Another cool feature is that you can use density on your UMAP, as we were doing before, density, and use another multiplots type. This is color by all. Okay, again, you can select whatever. In this case, FCS Express will take care of creating multiple copy of the UMAP and will color each copy based on the expression of the marker that you select here. Okay, I will click OK, and now you see I have my 3 UMAP. You can also activate the legend. I usually do it because otherwise you don't know which is which. So let's say the legend at the bottom. Okay, so this is something that you can do with any type of data. I'm dealing with image data, but actually you can do it with any type of data. And you see here, we can clearly see that, for example, this guy, it's CD4 and C and FoxP3 very bright. It's KI. It depends. I see some blue, some green, and whatever, but at least it's there. So this is another way in which you can analyze and explore your data. I think I will show you one more things, which is the histogram with overlay. Sorry, the parameter overlay histogram. So let me convert this to be an histogram, okay? And let me show, for example, the FoxP3, okay? So what you see here is the FoxP3 distribution of those events, okay? If I move my gates here, okay, I can see something different, okay? I can, of course, I can set it to log, okay? And we already know that those are FoxP3 positive, okay? If you scroll around, you can see negative, 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 positive. Now, if you right click here, you can add parameters overlay. So the idea is that you will add multiple overlays. Each overlay will display the distribution of a specific parameters. What's the advantage? The advantage is that you will see basically the phenotype, okay, of the gated cells in that histogram. And here we go. When you see something like this, it's because the legend is too big. So I usually either remove the legend or the y-axis parameter. Okay, it's up to you. So if you want to remove the legend, just go to the legend and make it invisible. That's fine. If you want to remove the, let's say we want to do the opposite, I will go to the axis, y-axis, and I will remove the title. Okay, it's up to you. You don't need both usually. And now you see that I can, let's put it down at the bottom. Okay, now I can see the phenotype of my gated cells. So it's just another way in which you can navigate through your UMAP or tSNE or whatever plots. So one way is the backgating, first thing that we saw. Second one is density plot and multi-plots, color by all. It means that multiple density plot with UMAP, each density plot is displaying a different color based on a different parameter. And last but not least is this overlay, parameter overlay histogram. Okay, is there any question? Okay, and let me close this, and I will conclude by saying that we also have clustering. We will not have time today. You see here we have predefined algorithm, okay, here. Those are FlowSOM and SPADE. We have also single algorithm like consensus, hierarchical, k-means, self-organizing map. All together, okay, can be used. And usually when you want to plot the results of those algorithm, you may want to use these. So the graph layout and minimum spanning tree goes together, and they are the one that are useful to plot your clustering as a tree. Okay, exactly as we say before. You might have these three, blah blah blah. So all those nodes are the clusters, okay, and the graph layout and the minimum spanning tree are the two guys that are creating this tree map for you. So last thing that I want to show you, it's very, very quick, is in the miscellaneous tab is the parameter removal. Okay, it's useful if you want to I mean, you know, in the pipeline, you might generate a lot of parameter, okay? If you have like 20 and you scaled all of them, you will have 40. If you then normalize those scaled, you will have 60. And then you will have UMAP 1 and 2, tSNE 1 and 2, and blah, blah, blah. You will have like 70. But maybe at the end, you do not really need the scaled and the normalized. I mean, those parameters were useful in the to actually run the pipeline, but those are not really useful at the end for you. Okay, this is another example from another instrument. And you see here I have my tSNE. Okay, I did the same as usual, a scaling, a tSNE, and UMAP. This is my tSNE, this is my UMAP. Those are like a parameter overlay histogram. The one at the left is gated on my tSNE, the one at the right is gated on UMAP. And I also have my picture, as you can see here. Okay, but anyway, the point is that here I have access to all the original parameter and also to the scaled parameter. Okay, in this case, they are just 7. But if you have like 20, you will have 20. And if you have scaled and normalized, you will have 40 more. How to remove them? Okay, I will uncheck the automatically run pipeline and I will add in queue my parameter removal step. So at this stage, the parameter removal has access to all the parameters generated by the scaling, tSNE, and UMAP. Of course, I don't want to remove tSNE and UMAP parameters. Those are the key point of my analysis. But if I do not need to access those scaled parameters, okay, in my plots, okay, I can remove them with this parameter removal. Okay, now I can go back. It will be rerun, okay? So every time you change something, FCS Express will rerun the pipeline. This is to be sure that whatever you see on the display on your screen, it's up to date. And now you see I have my UMAP, I have my tSNE and whatever, but I do not have here the scale. So this leads it's shorter, okay? Another thing that you can do with the parameter removal is just have one pipeline with just the parameter removal. Let's say that you have exported from your instrument like 200 parameters just to be sure that you have access to them. But then it's a pain to scroll between 200, and maybe you want to remove all the integrated intensity or all the whatever. Just create a single parameter removal step and apply the pipeline everywhere. Okay, so this was another example of pipeline step. But we really have a lot. So just to conclude, we wanted to provide you with the ability to create pipeline in a very user-friendly environment, which is the FCS Express FCS Express environment. Okay, so easy to use, really fast. I will never repeat this enough. So all these steps are coded into the same language in which FCS Express is coded. Okay, we are not copying from our Python, whatever. We do have the R integration, okay, for those who really want to develop something customized, but all the steps that you see here are coded within FCS Express, and they are super fast. So we are usually like between 2 and 10 times faster than every other software in running, like tSNE, UMAP, and FlowSOM, and all those stuff. And then you have the ability to combine multiple steps. It's really reproducible because everything is saved, and it's integrated because if you want, you can create, run the pipeline, and then access the spreadsheet. We will not have time to see this, but access the spreadsheet, create heat map, create charts, bar plots, whatever. Everything inside FCS Express. So if you have never used FCS Express and you want to give it a try, just go on our website, click on demo. Okay, it's one of the first links that you see at the top, and you can download the 30 days trial and do everything you want. If you have any question, just send us an email. So we are spread in 5 different time zones at the Novo Software. Basically, even if you're working at 1 a.m., no let's say it doesn't matter where in the world, we will be able to answer you. So feel free to write us at support@novosoftware.com with any question you have.